In the vast expanse of our solar system, there exists a storm so bizarre, so geometrically perfect, that it seems to defy the laws of nature itself. This is Saturn's North Pole, home to one of the most mysterious phenomena ever discovered in space, a massive hexagonal storm that has puzzled scientists for decades. Let this sink in. This hexagon is twice the size of Earth. Each of its 6 sides spans roughly 7,000 miles, a distance greater than from New York to London. When the Voyager spacecraft first spotted this formation in the 1980s, scientists thought they must be seeing things. How could a storm form perfect straight edges and precise angles? In nature, storms are chaotic. They spin in circles. They meander. They dissipate. They don't form hexagons, except here. Even more baffling is its stability. This storm has maintained its 6-sided shape for at least 4 decades. Possibly much longer, withstanding winds that reach speeds of up to 300 miles per hour. The hexagon isn't just a surface feature. It extends deep into Saturn's atmosphere, like a massive spinning cylinder of gas with 6 perfect sides. Look at these corners, they're sharp and well-defined, as if drawn with a cosmic protractor. No other known storm in the solar system displays this kind of geometric precision. What we're looking at shouldn't exist, at least according to our traditional understanding of planetary weather systems. While Jupiter's famous Great Red Spot swirls in a predictable circular pattern, Saturn's hexagon stands apart as a mathematical anomaly in the cosmic ocean, challenging everything we thought we knew about planetary atmospheres. To understand why Saturn's hexagon is so shocking to scientists, we need to look at how storms naturally behave throughout the universe. In nature, spinning fluids naturally form circles. This is true whether you're looking at water going down a drain, coffee being stirred in a cup, or massive storms in a planet's atmosphere. Take Earth's hurricanes for example. Every single one, from the smallest tropical storm to the most massive hurricane, spins in a circular pattern. This is due to something called the Coriolis effect combined with basic fluid dynamics. Even Jupiter's Great Red Spot, which has been raging for centuries, maintains a predictably oval shape. This is exactly what our physics equations tell us should happen with large-scale atmospheric movements. But Saturn's hexagon breaks all these rules. It's as if someone drew straight lines in the clouds and told them to stay there. The physics we understand tells us that high-speed winds should smooth out any angles. Sharp corners should be impossible to maintain in a fluid system, especially one with winds stronger than any hurricane on Earth. Yet here we see these corners persisting, decade after decade, remaining sharp and well-defined despite being bombarded by massive turbulent forces. What makes this even more perplexing is that Saturn's atmosphere isn't solid. It's made up of layers of hydrogen and helium gas, becoming progressively denser as you go deeper. There's no solid surface to guide or maintain this shape. This suggests there must be forces at work that we don't yet fully understand. Through Saturn's long seasons, intense storms, and varying temperatures, the hexagon remains. It's as if some invisible cosmic geometry is at work, forcing this massive storm system to maintain its 6-sided shape against all odds. Scientists now believe the answer might lie in hidden wave patterns within Saturn's atmosphere. But even this doesn't fully explain how such a massive system maintains such precise geometry. The Cassini spacecraft's 13-year mission to Saturn gave us our most detailed look yet at this mysterious hexagon, and what it found was absolutely mind-blowing. Before subscribing to our channel for more space mysteries, let me show you something incredible that Cassini discovered about this massive structure. Using its infrared instruments, Cassini revealed that the hexagon isn't just a surface feature. It extends downward into Saturn's atmosphere for hundreds of miles, like a massive hexagonal tornado reaching deep into the planet. Perhaps most surprisingly, Cassini showed us that the hexagon changes color with Saturn's seasons. During the planet's long winter, it appears a brilliant blue, but as spring arrives, it transforms into a golden hue. These color changes aren't just for show, they tell us something fundamental about how this structure works. Cassini's infrared cameras revealed that these color changes correspond to temperature variations and the formation of hydrocarbon haze particles in Saturn's atmosphere. The spacecraft measured winds around the hexagon reaching speeds of 300 miles per hour. That's faster than the most powerful hurricanes on Earth. Yet somehow, these intense winds don't tear the hexagon apart. At the edges of the hexagon, Cassini spotted countless smaller vortices, like tiny hurricanes, that seem to help maintain the overall structure rather than disrupt it. But the deeper Cassini looked, the more questions emerged. The mission revealed that the hexagon appears different at various wavelengths of light, suggesting it's not just one layer, but a complex structure that changes with depth. In its final dives, Cassini captured these incredible details of the cloud structures within the hexagon, showing intricate patterns that seem to defy our understanding of fluid dynamics. After decades of observation, scientists have begun to unravel the mystery of Saturn's hexagon through an unexpected source: laboratory experiments. In labs across the world, researchers have discovered they can recreate similar geometric patterns using simple rotating tanks of fluid. These experiments have provided our first real clues about how Saturn's hexagon might form. The key appears to be the interaction between faster and slower moving bands of fluid. When one layer of fluid rotates significantly faster than the surrounding fluid, something remarkable happens. Under the right conditions, the boundary between these different speed zones doesn't remain circular. Instead, it breaks into geometric patterns, including hexagons that look strikingly similar to what we see on Saturn. The exact shape that forms depends on a critical factor: the difference in rotation speeds between the fluid layers. Smaller speed differences tend to create patterns with more sides, while larger differences create shapes with fewer sides. The conditions on Saturn appear to be perfect for maintaining a six-sided shape. The similarity between these laboratory patterns and Saturn's hexagon is uncanny. Both maintain sharp corners, both rotate as a single structure, and both show remarkable stability over time. At each corner of the hexagon, tiny vortices form that actually help maintain the shape. These spinning pockets of fluid act like ball bearings, keeping the corners sharp and stable. What these experiments reveal is that geometric patterns aren't just human inventions, they're deeply embedded in the mathematics of fluid dynamics. From honeycomb to cooling lava flows to Saturn's pole, hexagons appear throughout nature when conditions are right. They represent a fundamental pattern that emerges when forces reach a perfect balance. On Saturn, this balance occurs where the polar jet stream meets the surrounding atmosphere. The massive speed difference between these regions creates the perfect conditions for hexagon formation. Saturn's hexagon isn't just a curiosity, it's forcing us to completely rethink how planetary atmospheres work. Now that we know such precise geometric patterns can exist in planetary atmospheres, scientists are revisiting strange formations seen elsewhere in our solar system, wondering what other geometric secrets might be hiding in plain sight. Our old models of planetary weather assumed storms would always take circular or oval shapes. Saturn's hexagon has shattered that assumption, leading to entirely new mathematical models that account for geometric pattern formation. The implications extend far beyond Saturn, affecting how we study distant worlds. As we scan the atmospheres of distant exoplanets, We're now looking for signs of similar geometric patterns. These could tell us crucial information about wind speeds and atmospheric composition on these far-off worlds. The hexagon has taught us that a planet's rotation speed and atmospheric composition can create unexpected stable patterns. This insight is revolutionizing how we model alien atmospheres. Even in our own solar system, we're re-examining mysterious features like Neptune's dark spots, wondering if similar physics might be at work there, hidden from our current instruments. The hexagon reminds us that the universe is, at its heart, a fluid place, following mathematical rules we're still trying to understand. By continuing to watch Saturn's hexagon, we're learning how these massive atmospheric structures can remain stable over decades, providing clues about long-term weather patterns on other worlds. Every new discovery about Saturn's hexagon gives us another tool for understanding the complex dynamics of planetary atmospheres throughout the cosmos. The mystery of Saturn's hexagon shows us that even in our own solar system, there are still phenomenal discoveries waiting to be made. Thanks for joining us on this exploration of one of space's most puzzling features. If you enjoyed this journey through the cosmos, don't forget to subscribe for more fascinating space science. Until next time, keep looking up, the universe is full of surprises.